In this video, we want to investigate the reciprocal function, which is the function y equals 1 over x. This is one of our most common rational functions. Remember, to be a rational function, you have to be in the form of a polynomial divided by another polynomial. And so because 1 is a polynomial as well as x, this counts as a rational function. So let's begin by making a table to see what this function looks like. Remember, we're trying not to rely on technology right now. So you can go ahead and make your table. And you can go ahead and begin from -2 to 2, like we typically do when we're beginning to graph a function that we are unfamiliar with. So let's go ahead and substitute in -2 for x. So substituting in -2 will give us -1/2 for our y value. Substituting in -1 will give us -1. But we do have a problem here when we substitute in 0. 1 divided by 0 is undefined. So that tells us that we have a domain restriction. 0 is not in this function's domain. Substituting in 1 divided by 1 gives us 1, and 1 divided by 2 will give us 1/2. So you can see here the nature of these values. What I substitute in for x, I get out the reciprocal, hence the name the reciprocal function. So let's begin with these values and graph what we have so far. So at -2, we have a y value of -1/2. At -1, we're at -1. 0 is undefined, and then we have +1, 1, and 2, 1/2. So right now we just have these 4 coordinates, which is clearly not enough to see what's happening graphically. What does this function look like? So we probably need to extend our table here. So why don't we begin by putting in some larger x values, say something like 3, 4, and 5. So inputting +3 would give us 1 over 3, or 1/3. +4 will give us 1/4, and 5 will result in 1/5. So graphically, let's see what's happening. At +3, we're just barely above the x-axis at 1/3. At 4, we're barely above at 1/4, and 5 at 1/5. So you can see what's happening as we travel to the right. As my x values get larger, my y values are getting smaller, but they're getting tinier, approaching 0. So we have the behavior to the right that looks like this. This part of my curve is just going to cruise along that x-axis and get very, very, very close to it. It's hugging the x-axis because we're getting these fractions that are very, very small, but they're still positives. Now think for just a second what would happen if I adjusted my table to include, instead of 3, -3, -4, and -5. Let's go more negative. And you'll see that my y value then, of course, would be -1/3, -1/4, and -1/5. So going to graph those coordinates, at -3, I'll be down at 1/3. Try that again, down at 1/3. At -4, I'm down at 1/4. And -5, I'm at a -1/5. So the left-hand behavior you see is very similar. We're going to have, let's try that again, sorry. As we go to the left here, my y values are getting larger, but they're still approaching 0. So this part of the graph is, again, hugging the x-axis, getting very, very close to it. But we're still not quite sure what's happening in the middle region here. So now we need to take a look at this inner region, and these would be the values that are between -1 and 1. What's happening there? So I've made some room in my table just because I'm out of room on this particular page, but you of course can just extend your table or just make a second one. We need to take a look at what's happening between, let's say, -1 and 1. Let's just start with the positive side. We know at 0 the function is undefined, and we know at 1 the y value is 1. So let's take a look at what's happening, let's say, at 1/2, or 1/3, and 1/4. All right, so the x value is 1/2. So as I input that, I'll put my work over here. 1 divided by 1/2. This is a complex fraction. 1 divided by 1/2 could be written this way, 1 divided by 1/2, which we know is the same as 1 times the reciprocal of 1/2, which would be 1 times 2. So when I input 1/2, I get a y value of positive 2. All right, let's do that again for inputting 1/3. So 1 divided by the fraction 1/3. That's going to be the same as 1 divided by 1/3 using my division symbol, which is the same as 1 times the reciprocal of 1/3, which would just be 3/1, or just plain 3. So I know when I put in 1/3, I'm getting out a y value of positive 3. And then you can see what's happening each time. I'm going to put in 1/4, and I'll get out a y value of positive 4. Once again, noticing that for every value that I input, my output is the reciprocal of that value. So now let's plot those points. So when my x value is 1/2, I'm going from the origin right 1/2, I'm going to travel up 2 for my y value. When my x value is 1/3, right 1/3, I'm going to travel up 3. And right 1/4, I'll travel up 4. And in fact, you can see as I keep inputting smaller and smaller x values, they're still positive values, they're very close to 0, I get larger and larger y values. So I have this behavior on my graph. We'll try that again. We have this behavior on my graph where this piece of the graph is going to go up, getting larger and larger y values, but again, the x values are getting closer and closer to 0. Once again, if we take a look at the negative side, if we were inputting negative 1/2, negative 1/3, and negative 1/4, that would just result in a negative output. So we can go ahead and graph those coordinates. -1, -2 is my output. -1/3, go left 1/3, that would result in going down 3, and left 1/4 would take us down 4. So again, you can see you have a very similar behavior, but now my y values are getting more and more negative as my x values get closer and closer to 0. So here we have the reciprocal function. We say that this function has 2 branches. Now let's take a look at the end behavior of this function. So we'll start with the left side of the graph. When we're looking at end behavior, we're going to be looking at what's happening as we travel along this graph, but going to the left. So that means we'd be looking here at the left-hand branch, specifically the far left side of that branch. So the way we would write this mathematically, our end behavior, we're saying as x approaches, and we use this arrow notation for approaches, as x approaches negative infinity. That means I'm traveling to the left on my curve. So pretend like you're a little ant on this curve, and here I am traveling on the curve to the left. What's happening to my y values? Well, previously we've studied polynomials, and for the polynomial functions, we know the only options for the end behavior were either the graph was rising or the graph was falling. But you'll notice if I'm an ant traveling along this curve to the left, my graph is not rising to infinity, nor is it falling. My y values are definitely getting larger, but you'll see that we're leveling off here, so my y values are getting closer and closer to 0. So we say as x approaches negative infinity, my y values approach 0. They get closer and closer to 0. So this would be considered the left-hand behavior. And then we can do the same for the right side. Let's analyze the right behavior as x approaches positive infinity. So now I'm going to be traveling on the right side of the graph. So as I travel, I'm on the right branch, and I'm traveling along the curve going to the right. What's happening to these y values? These y values are getting smaller and smaller, but they're not going down to negative infinity. No, they're getting smaller and smaller, and they're approaching 0. So we would write as x approaches infinity, my y values approach 0. This is how we'd write our end behavior, and this would be a new end behavior for us because, again, the end behavior is not simply just rising or falling, but rather the end behavior is that the y values are approaching 0. There we go. So what this information is giving us here, this end behavior, the fact that our y values are approaching 0, this tells us that the graph has a horizontal asymptote. I'll abbreviate, a horizontal asymptote. So a horizontal asymptote, you can think of it as an imaginary line, and I always graph my asymptotes in a different color because they're not actually part of the graph, but rather they are impacting the shape of our graph. It's this nice horizontal line that the graph is getting very, very close to. In this case, it's getting very close to that horizontal asymptote. It's not actually going to intersect or cross through that horizontal asymptote for this particular function. And the equation for this horizontal asymptote is the horizontal line y equals 0. So our end behavior tells us that we have a horizontal asymptote. But now, if you take a look at what's happening, not just on the ends of the graph, but actually take a look at what's happening here in the middle, you'll see that for this particular graph, we not only have a horizontal asymptote, but we also have a vertical asymptote. We have this imaginary vertical line that the branches of the graph are also getting very, very, very close to, but not intersecting. So we can add that to our list here of items. So the vertical asymptote for this function would be the vertical line x equals 0. So the reciprocal function y equals 1 over x has both a vertical asymptote as well as a horizontal asymptote. And then lastly, let's go ahead and talk about symmetry, since that's something that we have discussed already. This function definitely has symmetry. And perhaps you didn't even think about it before, but now that we've made a table to graph it, you'll notice that this function, if you were to take the branch here in the first quadrant and rotate it 180 degrees, you would get a matching branch here, an overlap, in the third quadrant. So that type of rotational symmetry, remember, that means that our function is an odd function, so it has origin symmetry. So we can say we have origin symmetry, which implies that my function is an odd function. Odd functions have origin symmetry. And if you need that quick review of how to actually check for this algebraically, remember, if the original function, instead of calling it y, I'll say f of x. If the original function 1 over x was f of x equals 1 over x, then we would go ahead and input a negative x value to check for whether the function is even or odd. So when you input a negative x, you get 1 divided by negative x, which you notice is the opposite of the original function. So when we get the opposite out here, that's telling us that the function is an odd function and it has origin symmetry. And that's a really useful fact, because now that we realize that, our table of values should make a little bit more sense, and you can save yourself some time, because if you know where one branch is, then due to the symmetry, you immediately know where the second branch is. So that's a summary of the function y equals 1 over x. Characteristics that you really want to remember: it has a horizontal asymptote, y equals 0. It has a vertical asymptote, x equals 0. We certainly have a domain restriction. The denominator cannot be equal to 0. And it's an odd function. It has origin symmetry.